You can introduce the session, Martin.
Thanks, Mike. Sorry about that. Jumping the gun there. So delighted to welcome everyone to this first block of parallel sessions. A very warm welcome to our session on LISA data analysis. My name is Martin Hendry from Glasgow University, and it's my pleasure to welcome our speakers for this session and indeed our audience for this session. Our numbers have been growing steadily for the last few minutes. So you're very welcome. The format, unlike our plenaries, which are in LISA webinar format and Zoom webinar format, this time we're back in just regular Zoom meeting. So that means that when we come to Q&A, people can feel free to unmute themselves and indeed switch their cameras on if they wish and ask their questions. But I would invite you to use the chat to ask questions if you prefer. That's a good way, for example, to ask questions as we go along, but we won't interrupt the talks. We'll keep the questions until the end of each talk, just to make things more manageable. We also are live streaming on YouTube. There may be some questions will come in from there as well. So I will do my best to field all of those. Just a quick word to our speakers. Let me note that we have 20 minutes allocated for each talk. So that's nominally 15 minutes of talk plus 5 minutes of Q&A time. So I will let you know when you've got 2 minutes left. And frankly, there's probably no easier way to do that than for me just to say that out loud. It saves you having to worry about keeping an eye on the chat. So I will do that. I will try not to be too rude and interrupt you midstream. But we are in fairly good shape time-wise for this session, because in fact there are only 5 talks in this session. So we've got 3 before the break and then 2 after the break. So it's LISA data analysis. We have multiple data analysis sessions. This is the first of 3. And before the talk, we have, before the break, we have talks from Stas BABAK, from Michael KATZ, and from Sayantani DATTA. So it's my pleasure to introduce our first talk, which is Stas BABAK from the APC CNRS in Paris, who's going to talk about global fit, find, remove, iterate, and enjoy. And I'm sure we will all do the enjoy part, as Stas tells us about the first 3. So thank you very much, Stas. Over to you.
Thank you, Martin. Let me try start to share my screen. Share and slideshow. One more second. Laser pointer. Can you hear me and can you see me well?
Yeah. Loud and clear.
Very good. So let me start. And this work was done in collaboration with quite a few people. And Silvia is actually giving a talk that's the person here, and other parallel session right together with me. I will introduce global fit in LISA data analysis. I know that Tyson did a great job yesterday. I really enjoyed listening to him. But nonetheless, let me just give you a few bullet points. So why we need a global fit and what is global fit? The thing is, LISA will be signal dominated, and we will have many gravitational wave signals, thousands of gravitational wave signals, and many of the signals are long-lived. So some of them will be living present in the data throughout the whole mission. Some of them, like massive black holes, will last from, let's say, a few hours to a few months. But all in all, we have a lot of signals. They overlap in time, they overlap in frequency. Some of them talk to each other so they can see each other's presence. Some others don't. And therefore, just going after one signal at a time and ignoring others, it would be wrong things to do. And we know about this. And that's what this global fit is about. In addition to all of this, that we have very rich astrophysical content, we will have, in resolvable signals, we also will have signals which are from unresolved, in the meaning that, those are signals which are, let's say, subthreshold events, subthreshold gravitational wave signals, which we're not confident about its detection and whether they're present or not, and therefore they will contribute to the total noise budget, and sometimes they actually exceed the instrumental noise. And in addition to this, we do expect some non-stationary features in the data, like gaps and glitches, and the noise level itself is breathing, will be function of time. And of course, we might have big surprises in LISA, like we did for first gravitational wave detection with the LIGO detector. And this surprise could be in the wave rate and in the parameter distributions. So let's move on. I will go quite quickly across this because Tyson already introduced this. This is the data called Sangria, where we actually probing our global fit. It contains instrumental noise in red. It contains verification binaries in yellow. This time the main data. It contains 30 million of galactic binaries. Of course, most of them are not detectable, but they will create the stochastic signal, which I mentioned before. And we have this in purple massive black hole mergers. If you zoom in, so sometimes you can see this is signal plus noise, but the signal is so loud that you don't even see the noise. Some others are much quieter, and you see they're actually below the noise. And if you look in time frequency, you can see clearly the tracks, chirping and merging tracks of massive black holes, and you can see horizontal lines corresponding to the most bright galactic binaries. So this is our playground. So those are signals, these are emerging black holes. And let me first introduce you a global overview before I go into details. So what we are trying to do, again, Tyson did a great job introducing, one variant of this global fit. I'll give you a slightly different variant of this. We start with the data. We pre-process the data so that and we analyze it visually like we just did it right now. We see already massive black holes. We see some galactic binaries. And what we see the most is this bright mergers of massive black holes, what we call elephants. So what we want to first to do in this step is we want to remove these elephants from the data and then go after something a bit weaker. And so what we'll produce is reduced data. I call reduced data is data, or sometimes it's called also residuals, is data minus some gravitational wave signals. And then we will make two parallel steps. We're searching for galactic binaries, and we will be searching for massive black holes. And we consolidate the results, and we check whether we are done or not, and we iterate this step again and again until we're done and save the data. So, and I'll now go a bit more into details of each step. I'll start with this step. It's what I call divide and conquer, or removing elephants. So as I said, we have these bright massive black holes mergers, and they clearly visible, especially if you whiten the data, or in other words, you apply a filter which removes high and low frequency component of the noise. You can see even the weak signals becomes visible in whitened data. So it's just visual inspection. You can see how many signals there. What you can do, you can, well, you still need to remove them, right? And I want to do it preliminary, not very accurately first, just to the level of the noise. So I will take a chunk of the data around this each merger, which I see by eye, around 2 weeks, and I will have very crude but very preliminary, very approximate gravitational wave models, which neglects laser motion, which neglects Doppler modulation. So I will not have sky location, and I also maximize over many extrinsic parameters. So I will be only having masses and spins, which I will be fitting for. And still, I need to find this masses and spins of these massive black holes, merging massive black holes, and I use a grid-based method with mesh refinement based on the Vegas algorithm. It's something similar to when you're trying to produce histogram, and you start with the equal bin size, but then you resize the bin according to the number of events, or in this case, and according to the likelihood in each evaluated at each this hyperbox, and then you resize it according to preserve the probability in each hyperbox. So it's something similar to when you're trying to plot this histogram by doing different bin size. And that's what happens. You start with the equally distributed grid, and after a few iterations, very fast, after a few minutes, you will have this refined grid where you see the more dense point where there is a higher likelihood and less dense point when there is no signal. So that's one of the methods, and for more details, you can look at the pre-recorded talk by Sen Van Deng. Alternatively, you can start with just stochastic method and run your favorite stochastic method like Markov chain Monte Carlo or genetic algorithm, and you're trying, here's an example from Sylvain, when you're trying to run a stochastic Markov chain Monte Carlo. Again, very crude, but you already see the signal and you preliminarily see where the parameters are. Now you want to restore the extrinsic parameters. What you can do, you can start with the already preliminary guess from the previous step, when you know intrinsic parameters, so masses and spins, and you run another Markov chain on the extrinsic parameters, and that's what you will get very fast. Again, these steps usually takes between few minutes to a few 10 minutes. So, and that's allows you to remove elephants to a very high level. So you can see slightly residuals here, but I don't care because I will be refining the search results in a minute. I managed to remove elephants down to the size of the cat or dogs, and now I'm good to make next step. In the next step, I will be searching independently for galactic binaries and massive black holes refinement. And then I will consolidate result and iterate. So for galactic binaries, similar to what Tyson has presented, we split data in frequency bands, roughly around 1 microhertz. It's a very narrow band. However, we're keeping the boundaries flexible. So let's look at this black segment here. There is also a red segment there and neighboring purple segment there. And our boundary is actually semi-flexible because we will be looking at the left and the right of the black segment. So what we're starting to do is, again, similar to what we did with massive black holes. We use F-statistics, so we're maximizing over some parameters of the binaries, and we're looking on a kind of grid for candidate events. So each candidate event will be followed by parallel tempering Markov chain Monte Carlo to refine its parameters, to find its better. And then first signal will be added to local catalog. And then we're going after second source. And every time when you're adding a source to the local catalog, we're checking if it has overlap with signals on the left and signals on the right, because we're running in parallel searches on each of these subsegments. If the signals are overlapping strongly with its neighbors, the neighbors are added to this pipeline to make sure we're not cutting signals in parts and having problems with fitting. Now, basically, it's again, we're adding signal by signal. However, it's not very good. So at some point, very quickly, when we're adding already two sources, we're actually running parallel tempering Markov chain with the two sources, making sure that if they talk to each other, they refine its parameters. When we're adding third source signal, we're again running on three signals, trying to make sure that all the correlations between signals taken into account. Moreover, we need to terminate this loop somewhere, and at each point when we're adding the extra signal, we're running model selection. So let's say our previous model had n signals, and we have another candidate coming up. So we're making model selection between n signals and n+1 signals based on the base factor. And if data supports n+1 signals is added. If not, we're terminating this loop at n signals and saying that's what we have found. And for details, I invite you to see pre-recorded talk by Eric Plagnuol. And so very briefly, results in a few frequency bands. So this is 4 millihertz. You see the color, the signals which we have found in the data, and this in the blue dashed and solid lines are residuals. Solid lines is what we found as residuals, and dashed is a theoretical limit, assuming that you could perfectly remove all the sources with a SNR larger than 8. The interesting part, you can see there is only noises seeing here and here. Everything else is basically covered by signals. When you're going to 5 millihertz, situation is slightly better. We start to have a bit less sources, but nonetheless, again, if you see the noises, noises are only partially seen in this frequency band, most of it covered by signals. When you're going to 6 millihertz, situation much closer. So basically, if you see dashed and solid lines very almost on top of each other, and we're recovering quite well signals. So between 3 and 6, that's what the most confused region of the parameter space, where the most signals are present. So next step is going right. Now we want to also to search for massive black holes. We already have preliminary parameters of these massive black holes, and we start from there. So we're not neglecting this. However, refining massive black holes is still non-trivial thing, even if you have preliminary guess. And we're making two tricks to make it happen, to find massive black holes very well. The first trick is if you look at the parameter space, so basically this is corner plot for parameters for massive black holes, you see a lot of correlations present there, and the structure of the posterior is very rich and quite non-trivial. However, you can do the mapping between physical parameters to some other parameters which easier to sample. So you see most of the correlations are gone, and they're more Gaussian looking posteriors. That's the first trick which we're doing. And second trick is thanks to Cornish and his postdoc in paper published in 2020. It's when they're suggesting so-called heterodyning likelihood in order to to speed up the calculations. What you do is like in heterodynamic, when you're removing carrier frequency, so the fastly oscillating part. Here we're not removing a single frequency, but we're removing the best guess of the signal. So basically we're removing evolving frequency in time. And at the end, what is left is residuals, which are slow changing function in frequency and in time. So that we basically, again, similar to radio technique, where you're removing the carrier signal. Here we also end up with a slowly low frequency component, which is much easier, requires much coarser grid in time and in frequency to sample, and therefore requires to speed up likelihood calculations tremendously. So these are the two tricks which we're using for massive black holes. Now, in a few more last slides, I want to introduce a few things which actually I did not mention. It's kind of swapped under the carpet, and now it's time to bring the carpet up and see what is underneath. So the first question is the noise level. The noise level is unknown. Even instrumental noise in this data is unknown. To some, it has some priors, but nonetheless, it's not exactly known. And moreover, the part of the noise is created by galaxy itself. So we need to evaluate the noise level. What do we do?
2 minutes left, Stas.
Thank you, great. We are starting with a guess for the noise level based on power spectral density estimation. And then at the end, when we found the signals, we plug a noise model with the found signals and reiterate it together. Some sources will be lost, some of them will be slightly enhanced, depends on our initial guess of the PSD. Then time iterations. The data comes every day, and we need to perform the analysis in time iterative way. And it looks like actually it helps, especially if you just analyze galactic binaries, adding data every 3 months. It's easier to look at the source when you have 3 months of data, and if you're adding more, you're just refining your already found parameters. And of course, the question, where do you stop the iterative procedure? And of course, since we know the answer, we can look at what is good enough based on the false alarm and comparison with catalog. When you don't have catalog, probably what we want to try to do is comparing parameter distribution between successive iteration steps and see when they stop evolving, they become stable. Or similarly, you can do residual comparisons. Of course, you need to penalize for introducing extra sources, extra parameters. However, this penalty should be not strong, because otherwise you start losing the relatively strong signals. And that's actually we already observe in our analysis. And my summary, so basically what we have demonstrated here is all necessary tools and steps to perform the global fit analysis. We have not finished it. Basically, what we need to do in the next steps is to make these iterations and complete the search. And what we need to test is also what the best noise model which would be easily fit into the residuals, and what would be stopping criteria of this iterative procedure. And I thank you for your attention, and I will be happy to answer questions if you have any.
Thanks, Stas. That was great. So are there any questions? Well, let me ask one to begin with. So you began by talking about the removal of the elephants. So can you comment on, how robust that part is? Presumably the rest of the analysis is not too badly affected if one elephant is left behind that is not removed?
Right. So in principle, nothing is really affected besides power spectral density. So we need to do some preliminary power spectral density estimation to start with. We did it for elephants, and then actually there was little iteration there, but not much. Elephants affect and strongly bias the power spectral density estimation, and that was that's why it was needed. And of course, you don't need to remove all of them. It just helps a bit, but not critical. But the brightest massive black holes, that's what is needed to be removed. But actually, it happens that we could remove all 16 or 15 sources.
Okay, thank you. Michael has a question.
Yeah, hey Stas, nice talk. I was just wondering, you said really quickly about the parameterization of your noise model.
Yeah.
I just wanted to know, just to clarify, if I understood correctly, that you're fitting parameters in the kind of parameterized noise model that we usually use, and not doing it kind of in your like sub bands or something and fitting a point, right? Is that correct?
So we tried to use in sub bands, but it turned out, so if you look at this data, that there are two solutions here. either noise only or noise plus signals. So you need to connect several bands, let's say like a 4 millihertz with 6 millihertz where noise is more visible. Otherwise, if you're trying to do piecewise in the small sub-bands, you will have, a lot of jitter up and down, especially in the part which is transition between fully confused to non-confused one. And so what we are trying to do now is really broadband noise models, which is has model for the galactic foreground plus instrumental noise at the higher low frequency parts.
Got it. Okay. Thank you.
Thanks, Michael. So are there any other questions? Well, let me ask another one very quickly. You mentioned towards the end the importance of not having too strong a penalty function because it could wind up removing sources. I'm not sure if I quite saw why that should be. Could you say a little bit more about that?
Yeah, so our approach penalty comes with the prior function, okay? Because therefore, it's if you're using very broad priors, you're allowing in a way a lot of false alarm to sneak in.
Yeah.
And as a result, what happens is that what we notice is our loose and broad prior, the limiting signal to noise ratio for galactic binaries was something 12, and which is relatively high. So when we're trying to do more astrophysical priors, we see that we can do better.
Yeah, thanks. Yeah, that makes sense. Okay, questions coming thick and fast. Let's see if we can squeeze two more in. Jean-Baptiste?
Yes, I was wondering, did you analyze the entire 4 years of data? And second question, how long did it take in total? What kind of architectures did you use? How many CPUs and so on?
Ooh. So it's a 1 year of data which we have. This is simulated data, and we analyzed not full, but we analyzed like 200 frequency bands of galactic binaries data. So we did not analyze whole frequency range. And then the question is how many size samples you want to accumulate.
Yeah.
So to find the signals, actually it is a relatively fast per frequency subband. So it takes like half day to few days per frequency band, depends on the frequency. And it's usually run on multi-core, single machine multi-core, similar to what Tyson has.
And so do you run each of the bands in parallel?
Yes, I don't know exactly how mod made talking to each other, because as I said, neighboring bands, they look at each other.
For the noise, yeah.
Yeah, not for the noise. It's for the even neighboring, if you're cutting signals in halves.
Okay. Thanks, Sess.
Great, I'm muted. Nikos, let's just hear your question before we move on.
Yeah, thank you, Stas. This was very nice. Just a quick one for my curiosity. So I think that you said that you are looking at overlapping segments, right? And then you're checking if there is sources that are in both segments. How do you do the classification? If how do you figure out if it's a source that belongs in both segments?
Yes, correlation.
Correlation. Yeah.
Overlap.
Okay, thanks.
Okay, thank you. Very nice one-word answer. So let's thank Stas again. If you can use the Zoom reactions, I will try to do that myself. And let's move on to our second talk, which is by Michael KATZ. So Michael, if you want to share screen. Okay, and Michael is from the Albert Einstein Institute in Potsdam and is going to talk to us about a new GPU accelerated adaptively distributed global fit algorithm. So take it away, Michael.
Thank you. So as Martin said, my name is Michael KATZ. I'm currently a postdoc at the Albert Einstein Institute. And today I'm going to be telling you about our new GPU accelerated adaptively distributed global fit algorithm, which I have been working on with Nikos Karnisas, Natalia Korskova, Jonathan Gare, and Nikolaos Sturgulaos. So I'm mainly going to highlight today, lucky for me, I've now gone after Tyson talked and after Stas talked, which has given me quite an introduction to the global fit. So instead of going through those kinds of things, I'm going to focus on what makes our algorithm different. So as you can see there in the first point, the main thing that we're going for here is to take important lessons from what Tyson and Neil have done, and then produce a new algorithm with it, one that can allow us to investigate different avenues of how to address this very computationally difficult topic. So these next bullet points here I'll address them in succession here as we go through the talk. These are all things that kind of make our algorithm a bit different, except for the last bullet point. I just want to make clear Tyson's codes are publicly available, and our codes are as well, as I'll talk about in my concluding slide. So the main underlying and underpinning aspect of our algorithm is we are trying to do this with GPUs. Now, the reason for this is, as Tyson said, and as you kind of heard a little bit there at the end from Stas, this is a very computationally difficult problem. And that's not a slight against anyone, obviously. This is just the fact of what we're working with. So what we are trying to do is we're trying to approach this from a different angle. And instead of trying to span it across many CPUs and CPU nodes, we're trying to understand the place of GPUs in this grand global fit scheme. So as you can see here, this is kind of our basic setup, but the reason we do this is we get hundreds or thousands of times faster from using GPUs. We do this by evaluating things in large batches and be basically loading as many of them as we possibly can. And in order to make everything extremely fast, or as fast as we can possibly get it, and as least memory intensive as we can get it, we end up using all residual-based single source likelihoods. So what that means here is, I think Stas kind of briefly mentioned it. It's where we take the current point of our sampler, we generate a template of all of the binaries that are currently there, and we subtract them out. And that's effectively gives us our residual, and then we do likelihoods against that residual. So the base likelihood, the regular likelihood we're used to, is up here in the top. So you would compute this after you have created this amassing of templates in the letter H here. If you add a source like we do in reversible jump, you can add it right here, like you see the letter A right here. And if you do the math, you can get to the point where you see that the change in the likelihood from the base likelihood is given by two single source likelihood terms. And what I mean here by single source is that you ultimately have to calculate the inner product across the width of a galactic binary spectra, which is not wide and is small, something like 256 points or so. So this ensures the fact that your integral or your discretized summation is very small and therefore very fast. When we are proposing a new point for a point that already exists, so we're not adding a source, but we're taking an existing source and updating it, that's effectively the same as removing the old source from the data and adding in a new source. So that's how you can see here, we have H plus A minus R here to represent kind of this changeover of the waveforms. And after you do everything out here till the end, you'll find once again that all of these inner products are single source with inner products that are all extremely, extremely fast. And is this kind of underpinning that we use to kind of design the rest of our sampling. So with that said, the GPUs give rise to what we are calling adaptive distributed Gibbs sampling. So similar to what Tyson and Stas have done in the band structure, I've kind of tried to schematically show that here. As you've heard, there are a variety of ways to set this up. There are a variety of ways to kind of pick your bands. But if I'm not mistaken, in Tyson's setup, and I think in Stas, you can please comment after if I'm wrong, once you have picked the bands, they're generally fixed and generally fix your computational resource distribution. And that is the kind of aspect that we're trying to look at, is how do we adjust this to be to pertain more towards GPUs and a ways of kind of loading the GPUs with as much information as we possibly can. So the way that we do that is on the fly, we want to assess which sources are independent of one another in terms of their frequency. And so we can see kind of an example here of that, where if we have our blue and our orange source, we cannot run these at the same time, because they affect each other, they're affecting the likelihood, depends on each other. So we cannot run the blue and the orange signals together. But as long as we do some very particular bookkeeping, we can run the green source and the blue source at the same time, because their effect on the likelihood is effectively independent. So with that said, what we do is we set up an algorithm to locate all of the binaries existing currently in our sampler that do not overlap with one another. So for example, in our first group, that looks like this, where we start with our first column. And just to be clear here, the vertical axis is walkers. So the rows are independent of one another already. But our goal here is to kind of maximize how much we can run across all of the walkers and within each walker all at the same time. So if we start here with this blue dot here, we check these first three. We notice that they are overlapping with this blue one, so we don't run those. We find this one is not overlapping with the first blue one, so we run it. Same thing with this one. We check this one. It doesn't overlap with this point, so we run it, and so on and so forth. So the idea here is to kind of iteratively build which sources are completely independent of one another and loading those all onto the GPU at a given time. So as we build this up, this is kind of what it looks like. We start to fill in until we have reached a full coverage over all of our existing sources. And what we do then is kind of, you can imagine it running like this, where now instead of farming out a variety of nodes for the different subbands, what we're trying to do here is kind of conglomerate everything and then split it up across GPUs so that we can keep everything as confined as possible. And part of our goal here, as I'll briefly mention in the end, is we want to try and get around this band structure, or at least minimize it. I think as I showed back here, we want to try no subbands or very wide subbands. So this talk from Stas and Tyson about this, we are trying to do this a little bit differently to investigate how running with or without subbands is useful effectively, and where we can leverage that to our advantage with the GPUs. And as you can see here, doing this type of setup gets us to running about 80,000 likelihoods per second on one A100 GPU. We could probably even make that a little faster with some of the setting choices that we've chosen. This is a bit conservative. But as you can see just from that number, that this is really, the GPU is a really nice workhorse and giving us kind of an alternate avenue for addressing the computational difficulty of this problem. Another really nice new tool that we use is called multiple try MCMC, and I will explain that in a second, but I will start by explaining just regular MCMC. So just as a reminder, you start with a set of parameters here in orange, you propose the blue set of parameters, you accept or reject it, you get the orange if it's rejected. You propose the pink set of parameters, you accept or reject it. In this case, you get the pink parameters. But ultimately, this kind of central line of blocks is your chain. These are accepted or rejected based on this acceptance probability shown here. Just in a simplified sense, you can think about it like the ratio of the likelihoods. So if the likelihood of the new point is better than the likelihood of the old point, it will always be accepted. If the likelihood of the new point is worse than the old point, then it will be accepted a fraction of the time. This fraction is governed by this ratio. Now, if we take a regular MCMC proposal that, for example, works 1 out of every 10 times, so you have an acceptance rate of 10%, which may sound low or something, but that's just for the sake of instructional purposes. But also, as Tyson talked about, it is quite difficult to design efficient reversible jump proposals because of the parameter space that we're dealing with. So just for this example, take that to be the truth that this proposal we're looking at succeeds 1 out of every 10 times. Roughly schematically looking, this is what your sampler would go through, where it starts with the orange blocks, and eventually you get 1 accepted where the blue moves over. Now, the thing that we're using, which is multiple try MCMC, is a bit more complicated than that, as you can see, but it's different and it's useful. So instead of proposing 1 blue point, we actually propose 10 of them at the same time. We then pick 1 of them as our actual proposal point by drawing based on its importance weight. And in this case, you can just think about it as the likelihood. So in other words, if we propose to say, for example, add a new binary, and we propose to add 10 of them at the same time, and only one of them finds one, that likelihood will be high, and that will be the one that will be selected out of this 10. Now, the catch here is that you can now no longer compare your new point that you have selected based on its importance weight against the old point, because you will not be satisfying detailed balance. Instead, you have to add 9 auxiliary proposals to add to the one original, so that you now have 10 proposals on this left side and 10 proposals on the right side. And your acceptance fraction becomes dependent now on the sum of the likelihoods of these groups, instead of on the singular likelihoods of the new and old point. And then you can see that down here, and that is literally the sum over the sum of each of them. Now, if you look at this, you may wonder why this is more efficient. You're actually computing 2 likelihoods for every one. So in this case, we want to do 10 proposals, but we actually have to calculate, it's really 19, but okay, we'll call it 20. We need to calculate 20 likelihoods here, effectively. But the thing is, with the GPU, because we want to shove everything onto it at once, it becomes much faster to do 20 likelihoods at once, for example, rather than 10 iteratively, sequentially, one after the other. So that's why this type of algorithm can be very useful when using the GPU and for reversible jump. And this kind of brings it all together in the kind of schematic returning to comparison with regular MCMC. This is obviously kind of simplified and not entirely true, but just trying to paint a picture here that if you propose 10 points for every proposal now, for a proposal that is accepted 10% of the time, you will actually propose an accepted point, on the average or whatever, each time. And what this does is it allows for much better mixing of the MCMC chains, I think better convergence in your sampler. And ultimately, I think it's just very good because we can, with GPU, really up the amount of proposals we're using, so we can extend this number of blocks per proposal, basically, and really draw in good proposals for reversible jump MCMC in an efficient way.
That's just about 2 minutes left, Michael.
Sounds good. Yeah, the last thing I will talk about is this SNR annealing search. So as Tyson has talked about, and also Stas, you got to be very careful about how you do the search. Instead of building up over time, kind of like Tyson has done, what we are doing is an SNR annealing setup. So don't worry about any of the numbers on this plot. This is just a schematic to be illustrative once again. So what we do, if you can imagine this gray block, the top of it is an SNR limit. And what we fix is so that the sampler does not allow any sources to exist inside of it that have an SNR below our SNR limit. So as I play this, you'll start to see the SNR limit go down. So this will be iteratively happening in our sampler. I'll pause really quick and just say, you'll see these popping up. They're not filled in yet because we rarely find these sources at their peak SNR, so at their peaks. We usually find them a little bit lower, and that usually comes in through the use of parallel tempering. So what you'll see now is they'll pop in here and show you that they're now detectable. But the key is, once again, we don't allow anything to exist that is below this upper limit. And now you'll see kind of the low SNR binaries pop in. So that's, really in a simplified way, that's what we're doing. We're just preventing low SNR binaries from adding in and messing up our search effectively in similar ways that Tyson and Stas talked about. So this is my concluding slide. So I'll just say a few things in conclusion. And the top bullet point there, you see kind of the main things that we have added to our global fit algorithm that makes it a bit different than Tyson and Stas's algorithm. What we are working on now is scaling up to maximize our source count per band. This is our kind of last successful trial we have on the right side, where we have about 50 sources. We're now running bands with 2,000 sources in them. And so far seeing decent results, but we're not quite there to, they're extremely preliminary. So that's why I haven't shown any of them yet. But ultimately that's what we're working on now, is trying to understand how this large band structure can benefit us. We're then going to do non-stationary noise effects for the LBC2A that Stas was talking about. And I'm going to implement a pipeline that I designed for a previous paper for the massive black hole part of the LBC2A, as Stas also alluded to. All of the waveforms and codes that we use are publicly available. The galactic binary waveforms are fully publicly available and available here. If you were at the LBC workshop yesterday, you saw and got a taste of this. The sampler, which we have, is a non-gravitational wave specific sampler, and a set of tools called LISA analysis tools are also publicly available, but they're in a beta version. So if you are interested in using them, please talk to me before you use the beta version ones. But eventually, as we kind of finish up, clean those up, add tutorials, add documentation, these will all be publicly available and for use by the community. And I would just like to end by saying we'd like these tools to be community developed. So if anyone's interested in doing that, please let me know. We welcome it. And I'm happy to take your questions. Thank you.
Thanks, Michael. Very interesting. Yeah, I'm not sure what happened when you heard the recording stopped. It seems to have restarted. It may have dropped out for a few seconds, but I hope it was still streaming to YouTube so we can patch that in. So are there any questions? Well, again, Content has one, so let's go with that.
Hi, thanks. Thanks, Michael, for this very interesting talk. I was wondering, did I understood well that you're grouping the calculations of non-overlapping sources because you're grouping the dot products and not the waveform computations themselves? Or so just to be a little clear there, because grouping, I think, has a couple meanings there with the GPU. Yes.
So what we are doing, so our goal is to basically make the largest group of sources that we can run at a singular time that can all be run independently in the current iteration of the sample. And then once we have, like on the wrong screen here, sorry, I'll just scroll. Hopefully I have that still up. So what happens is we basically conglomerate all of these groups into the largest groups that we can make, and we kind of iteratively run them across as many GPUs as we can, more or less. So we split them up based on their overlap, whether or not their signals overlap, but then we run all of those that don't overlap as a single entire group. And then we just do very careful bookkeeping. So what we're really doing is we're not calculating the likelihood, we're calculating the change in the likelihood. We do an accept or reject, and then we update the likelihood, the overall likelihood, and update the residual based on all of them that are updated in the same data stream, which I hope makes sense. I hope that answers your question.
Yes, okay. That you're updating the likelihoods, and this I had missed. Okay, thank you very much.
Thanks. Let's go to Christopher now. Christopher, are you there?
Not hear Christopher, although it doesn't say he's muted.
Hey, can you hear me now?
Yeah, we can hear you.
Okay, so great. Thanks for the talk, Mike. I was wondering about the annealing you showed and the fact that sources were only found after you got beyond the SNR peak.
Yeah.
And I'm just wondering, is there a relation between how much you need to drop before you find a peak? Does it vary across parameter space, whatever sources you've got?
So one thing I really haven't included here is for the really loud sources, we actually do a bit of an iterative subtraction to start, just because this SNR annealing part, if you want to be very careful about it, it kind of takes a long time to get from the loud SNR sources to the low SNR sources when there really aren't many of them. So just to be clear, some of like the loudest ones, we iteratively subtract up front. Once it gets down to the low SNR sources, that I think is where we have to be really careful, and that's where we have effectively mainly used this algorithm. I would say the one that we're running right now with the 1,000 source bands, we stopped at about an SNR of 50, doing the iterative subtraction, I would say. And then what we do is we just run this very slowly. And what we see ultimately is, once you get to the low SNR sources, obviously there's only so much SNR you can latch onto. So for those, it's not too difficult in terms of tuning this. I think the real thing where the real usage of this comes in is with parallel tempering. Some of the higher temperature chains, what they'll do is they will, lock on sources and then over time move them up. And then once they move up, that's when they shuffle down the temperature ladder. So I think maybe that's a better way to look at it is it's pretty hard to find them in the 0 temperature chain or in the temperature 1 chain or the cold chain because you're really already at the peak of the likelihood and you don't have a lot of leeway for putting that one source in. So I think I actually saw Neil say this in a comment yesterday during Tyson's talk, is we do see a lot of these kind of shuffling in at higher temperatures, adjusting slightly, and then once they're at the peak, they swap down to the cold chain effectively. So that's kind of how that's done. And I hope that was clear.
Yeah, thanks, Mike. So I guess we should move on. Sorry if there were other questions that we didn't get to, but let's thank Michael again. Thank you. And we'll move on to our third and final talk before the break. And if I can invite Sayantani to share screen.
Yeah, let me share my screen then.
And then we'll introduce you properly. Excellent. So it's my pleasure to welcome our third speaker, Sayantani DATTA from the Chennai Mathematical Institute, who's going to talk to us about enhancing the performance of multiparameter tests of general relativity with LISA using principal component analysis. So over to you, Sayantani.
Thank you. Hello, everyone. I'm Sayantani Datta, and I'm a graduate student at Chennai Mathematical Institute, working with Professor K.G. Arun. And I'm going to talk about enhancing the performance of multiparameter tests of GR with LISA using the method of principal component analysis. So to start with, we know that the detections of gravitational waves have allowed us to test GR at really high curvature regimes, and one runs into various problems while formulating a quantum theory of gravity in such regimes, and hence there are different modified theories of gravity. So there here shown is a brief classification of these various modified gravities based on Lovelock's uniqueness theorem, where each modified class arises from violating one of the underlying principles of GR. For example, there could be dynamical fields non-minimally coupled to G mu nu, or auxiliary fields to the stress energy tensor. We could also consider Einstein-Hilbert action in higher dimensions. Then there is weak equivalence principle violations due to non-minimally coupled fields to the stress energy tensor. And then, of course, there could be some form of diffeomorphism invariance violations. So given we had some theoretical model for gravitational waves emitted in these theories, we could have put them to test. But in their absence, what we do is do a parameterized test. So for this, we have a very good understanding of the gravitational wave phase evolution under post-Newtonian approximation of GR. So in this plot, you see the different phases in the evolution of the binaries, starting from in spiral, when the binaries are far apart from each other, and in spiral due to gravitational radiation reaction. So in this regime, the gravitational waves can be modeled using post-Newtonian approximation, and the schematic form is given in the first equation. And in the second equation, the basic structure of the phasing is given. So both the amplitude and phase can be expanded in powers of V by C, which is what is shown here. The phi k and phi kls are called the post-Newtonian coefficients. And these are all functions of the intrinsic parameters of the binary, for example, the mass, spins, and so on. So these post-Newtonian coefficients are quite rich in structure, and multiple nonlinear interactions and physical effects can enter in multiple post-Newtonian coefficients. For example, example, the tail, for example, the 1.5 pin coefficients has both spin orbit interaction contribution as well as tails of gravitational waves. So it's only natural to expect that multiple post-Newtonian coefficients may get modified if the binaries interacted differently in a modified theory of gravity. This gives us a motivation to test for these coefficients and see if they're consistent with the GR value. So for that, we introduce consider this null parameterization, where fractional deformation parameters are added at each PN order. These are denoted by delta phi A. Of course, in GR, their value is 0 and could have any non-GR value in the modified theory of gravity. So as I said earlier, we would actually like to do a test where multiple post-Newtonian coefficients are measured. So this will be called as a multi-parameter test of GR, where both the GR parameters along with multiple post-Newtonian deformation parameters are measured simultaneously. Now, this is a more general and a rigorous form of parameterized test. However, it's really difficult to do this because of the correlations between the deformation parameters. But we did show in these two papers that one can really do a full multi-parameter test where all the deformation parameters up to 3.5 PN can be measured, but using multi-band candidates. These are the stellar mass black holes on the heavier side and some intermediate mass black holes of the order of 100 that can be seen in both LISA and ground-based detector, and we can use information from both these places that help lift these degeneracies. However, the rates of such events would be really low. So what is now done is the single parameter test, where only one deformation parameter is measured along with the GR parameters. So this is a restrictive and approach, but a useful null test. However, this demands eight independent runs for a single event. So how do you actually overcome this problem associated with multi-parameter test? So since the main problem is the degeneracy, we could use principal component analysis to transform to a new basis where these correlations are basically gone. So in this new basis, we'll define a new set of parameters and we'll call them as PCA parameters. And we actually demonstrated this method on O102 events detected using advanced LIGO. Using a Bayesian inference, and we found that we could detect we could measure the first two PCA parameters well, and they could pick up the true value very close to the mean. But here what we will see if LISA can help us to measure more of these new PCA parameters, and in turn can help probe higher PN orders better. The relation between this, measuring more of these new parameters and probing higher PN orders will be clear as I go forward into the talk. So as an example, I have shown here posteriors on the deformation parameters from 5-parameter test using a system of 6.6 times 10 raised to 5 solar mass. So, so deformation parameters from 0 to 2.5 PN are simultaneously measured using Fisher information matrix, and we can directly get the errors from the covariance matrix. As you can see that the contours are all tilted, and it tells that the deformation parameters are highly correlated. Now, using the same system, I have performed a PCA on this posterior samples. So how that's really done is that I have taken the marginalized Fisher matrix for the same system, and I have diagonalized it using the equation shown here. This directly gives me the errors on the PCA parameters, which is nothing but the square root of the inverse of this diagonal matrix S. Now, if you do the same transformation to the likelihood, it's easy to compute that this PCA parameters are nothing but linear combinations of the original post-Newtonian deformation parameters, which is what is shown here. So this equation also tells that any measurement on the PCA parameter is also a simultaneous measurement on all the PN deformation parameters. So carrying out this transformation on the previous example, the contours are all axis aligned and the constraints are better. So this tells that the correlations between the PCA parameters are lifted, and in turn we have constructed best measured linear combinations of the deformation parameters, which are themselves null variables. So having introduced the method, I have computed the bounds on these parameters as a function of total mass, and I've used the IMR phenom-T model, which is in spiral merger ring down, which has only quadrupolar contribution and axis aligned spins. There are a few points to look at here. The first is, of course, that the leading two PCA parameters are very well measured, and they're denoted by the black and red lines. It's as good as of the order of 10⁵ for the leading one and 10⁻⁻⁴ for the red one. And another feature which is very clearly evident is that there is a clear hierarchy in the number of PCA parameters you can measure as you increase the mass of your system. It's really the lower mass in spiral dominated systems with which we can do this test best. And if you also keep in mind the accuracies, the errors on these parameters, the best events really are the ones around 10⁶. This hierarchy can also be understood in terms of the information that each of the PCA parameters carry. For example, and this information it can be associated with the corresponding eigenvalues of these PCA parameters. And if you plot them, it shows the similar hierarchy. It just tells that the information carried by the higher order PCA parameters are lesser and lesser as you go to higher masses. Yeah, and another feature is the structure. There are some features. There are some structures in the leading to PCA parameters, whereas the sub-leading one seem rather simple, and this can be understood once we look into the composition of these linear combinations, which is what is shown here. So let's first focus on the left-hand side plot, which is the leading PCA parameter, and the linear combination goes as U1 naught delta phi naught plus U1 2 delta phi 2 and so on. So this magnitudes of this U matrix, the magnitudes of the elements of this U matrix actually tell how sensitive is this PCA parameter to the original post-Newtonian deformation parameters. And that is exactly what I have plotted here. And the main take-home message from here is that the leading PCA parameter is mainly dominated by the first three post-Newtonian deformation parameters, denoted by this black, red and blue lines. The same applies to the second leading one as well, which is shown on the right. However, there is one interesting feature here is that as you increase the mass, the cyan line, which is 2.5 pn log, it pops its head out from the crowd. And and apart from this, the large number of undulations and in these weights are due to a complex interplay of the change in SNR, the change in number of cycles, the changing correlations between these different PN deformation parameters as you sweep through the frequency band. For example, these dips here are nothing but the weights going to towards the negative side because of complex change in the correlations. Yeah, so now let's look at the higher order PCA parameters, which are the subleading ones. So on the left hand side, we have the third dominant PCA parameter, and here the most striking feature is that the cyan line has really come out compared to the previous one here. This only gets more prominent as we go to the fourth PCA parameter, where the 2.5 PN log term dominates. And of course, there's again increased contribution from the 3 PN log and so on. So this only tells that as you are able to measure more of the higher order PCA parameters, you're able to probe the higher order PN, higher order PN coefficients better, and also with good accuracy because of Lisa's good sensitivity.
You have about 2 minutes left, Sayantani.
Sure, I'm actually done. So let me
Perfect.
just conclude. Yeah, so let me just conclude. So I have shown that with Lisa, you can measure up to 5 of the new PCA parameters, and these are nothing but the best measured linear combinations of the PN deformation parameters, and they help us to test the entire PN structure of the of the gravitational wave phase evolution. The most dominant one can be constrained with a 1 sigma error of the order of 10⁻⁵, while the second one of the order of 10⁻�3. And the third important point is that this PC assisted test of GR reduces a large amount of computational cost, because this is really one multi-parameter run, and the rest of the transformation is really post processing. There are a few things that I plan to do and is underway. One is analysis with higher modes waveform, because this plots show really more structures as you change the iota and eta. And this is really helpful in getting a sense of where, if we detect, suppose, a deviation in GR, deviation from GR with the help of one of these parameters, it gives you a sense of where is it coming from. So I also plan to do some MCMC runs with non-GR injections to see how well are these parameters able to capture those non-GR injections. So yeah, that's all I have to say. I can take any questions. Thank you.
Thank you very much. That's very interesting. So are there any questions? Or maybe I can ask one to begin with. So would you mind going back? I think it was 2 slides. It's the one where you were showing well, actually, any of these would do, the composition slides. Yeah, thank you. So I was thinking about PCA often being used as a data compression algorithm. So the relevant use there is to consider the different principal components and how much of the total variation in the data the first few principal components describe. So I guess that's kind of related to these plots, but not quite the same thing. So could you comment on that? Like how much of the total variation is described by the first few principal components?
Yes, actually, that is more evident actually from this plot. So this truncations that you see is nothing but what you said. The truncation is happening due to because we're choosing to drop the higher order PC parameters as they carry very less information, even less than. I mean, for example, for a system of 10⁻⁷, the first 2 PCA parameters capture more than 99.9% information. So the rest of, which is what makes the higher order PCA parameters not measurable, and we drop them. What I'm showing is really the composition of this PCA parameters, which is made up of all the 8 deformation parameters. original ones. But yeah, as you said, this part is really the data reduction in the dimensions that's happening.
Okay, and as you explained, that's a function of the total redshifted mass, as described in that plot. Yeah, thank you.
Yeah.
Are there any other questions? Quentin?
Yes, maybe one. I'm not sure I understood. Hi, thank you for this talk. I was wondering, so you are sampling for the PCA parameters, and you've shown as well that, of course, this PCA transformation depends on the parameters themselves. So how do you handle that, right? How do you sample for the PCA parameters, knowing that you have a parameter-dependent transformation? I think I didn't get that.
Yeah, so here we are actually not sampling over the PCA parameters. This is the sampling is done on the original post-Newtonian deformation parameters, which is basically this. Now we really take this, you can really take the Fisher or the covariance matrix of this and do the decomposition on that.
Got it.
That,
okay.
Yeah, and that gives you.
Okay, thank you. Yeah, I understand. Thank you.
Thanks, Quentin. So any final questions? Well, we are a few minutes behind schedule, so let us maybe stop there. But let's thank Sayantani again for a very nice talk.